Beautiful. So for anyone who's online, as a heads up, I will be flipping my laptop around and you're going to get a really lovely view up my nose. I don't really care. I've just accepted that, but I talk a lot with my hands. I want you to be able to see that. Um, and I can't see you. So if you have any questions or comments, please just unmute yourself. I know it's scary, but I believe in you. A quick introduction to me before we get started. So my name is Sarah. I use she, her pronouns. I'm in my 5th year of materials. I bio out of 6. I have only done summer co-op, so my degree is actually extended because I'm taking a minor in medical and biological physics. Outside of school, then I do a handful of fun things. Most notably, I am on the Materials Engineering Society, and I'm also on the varsity rowing team. So if you have questions about anything like that or getting involved, I'd be happy to chat. I also just wanted to put my email out here, and these notes should hopefully be sent out to you afterwards, because if you have any questions about materials engineering or anything else, I used to be a physics tutor, and I've been on a variety of clubs and teams in my time. I'm old and I've done a lot of co-ops, I've done a lot of resume review sessions, things like that. So if you have questions about anything, I want you to know that I'm here as a resource. I'm here as hopefully a semi-friendly face at the end of this, for anything that you may need. I would not have survived first year without the help of a number of upper years who kind of extended an olive branch, so I kind of want to do that and just give you my email there in case you have any concerns. Another thing that I want to do before we get started, have you guys seen this yet? Was this posted on Avenue? Beautiful, because I didn't see it on the Instagram yet, so I haven't reposted myself. But the materials department offers a materials engineering fellowship. What this is you apply for the fellowship, you submit, ooh, a statement of interest and a transcript. So your statement of interest is basically like a cover letter. And then there will be some sort of interview process. And it's saying like, why do you want to go into materials engineering? And if you're interested in materials, this is a really great opportunity because it guarantees you employment for your first 3 summers. Personally, being a materials fellow jump-started my professional development. I did not have any entrance scholarships and I could not find a single co-op after my first year, but I became a materials fellow and that got me into like kind of my foot in the door in terms of employment. Um, because it got me a research position and it got me kind of starting those networks. So I think it's a really great opportunity. Applications are due on the 13th of January, I think. Um, so yeah, really great opportunity. Wanted to flex that. Hi, friends. There's snacks in the back if you want any. My last thing that I'll say is that I know that this is listed as materials, ethics, and design. Personally, I found that what folks struggle the most with is materials, and that's also what I am best at. And Heike, Emily told me that I could just focus on materials, so that is what I've prepared. It's going to be talking about materials engineering, but if you have questions about anything else, obviously I did take this course many years ago. I did wellness course many years ago, so I can chat about that, and I have all of my notes from first year as well, so I can refer to those as necessary. Does that make sense? Beautiful. So kind of what I'm going to be doing. So I just did a bit of an introduction. I'm going to go over a few more things. I'll go over some general tips and tricks for the mid-year exam. Then I'm going to review some core concepts that I think are really important to your overall understanding of materials engineering. And then after that, we can do any sort of Q&A that you may have. But I cannot stay past 6 o'clock. If we do run out of time, then of course my email is always open for questions. I would so much rather answer your materials questions than study for my own exams. Um, yeah, and then my last disclaimers again before we get started. I am not a professor, I'm not a TA, I'm not an expert. So I can't guarantee that everything I say will be like 100% correct, but I have been in the materials engineering stream for quite some time, so I like to think that I have a decent concept of it. But you guys are also covering a lot different content than what we did in first year. Some of it's the same, but some of it's different. So I might not be an expert on some of the specifics to what you're doing. So some general tips for materials and for the exam in general is do the example questions that are posted and covered in lecture. My midterm for 1P10 and the final exam, some of the questions were exactly the same as those that were in the lecture slides. Like the numbers themselves were the exact same, which was crazy because ours was open book. But that's my biggest tip. In terms of materials engineering, I really suggest focusing on the understanding of the concepts, not just memorizing it. There's a lot of content, but if you can start to relate the concepts together, then that'll make it a lot easier. And I'm going to try my best to try and explain and show how all of these different concepts relate to each other. The exam can feel really long. I remember the 1P10 exam felt particularly long because there were so many different components in it, but just take a deep breath. I believe in you. You got this. And then the other two things are just to watch your units. Make sure you understand make sure you always include units in your answers and make sure you understand, like, for example, the unit conversions of newtons over meter squared versus newtons over millimeter squared. I know that really tripped me up back in first year. And then understand your formula sheet. So I know your formula sheet looks Yeah, so you have, I think you're given this formula sheet or whatever. It's really important that going into it, you understand what all these symbols mean, and like what they're called, so that when you see a question and you're asked to calculate, for example, the yield stress, you're not looking at your formula sheet being like, oh no, what equation do I use? And even if you don't know exactly how to solve something, you can quickly narrow down what the different options available for you are, based on, just looking at your formula sheet and understanding it. So those are my general tips. Now we're going to get started into kind of our main concepts here. So the big question that I want you to be continually asking yourself as we review materials engineering is, what makes each material different? What properties are changing? That means, like, what is happening in the material that changes its properties? So how is a metal different from a polymer? What is actually happening there? And how does that affect its behavior? So as we kind of go through this overarching question, then we're going to talk about the types of materials. Then we're going to get into bonding, stress and strain, fracture mechanisms, and strengthening mechanisms. I know you covered some topics other than that, but we only have so much time. And I think that these are the most overarching concepts in general. So if you have any questions or points, just like raise your hand, yell at me, whatever. The first thing we're going to talk about is types of materials. So there's three main types of materials. So we have types of materials. So the first one we're going to talk about is metals. We're all familiar with metals. We're really familiar. I want us to also like try and relate these back to things that we know. Like we're familiar with metals, right? Cars or, the size of whiteboards, things like that. They're all metals. We know that they're hard. We know that you can bend them if you try, like if you like bend a spoon or something. We know that they're ductile. We know that they can conduct heat because, for example, if there's a pot there, it's a metal pot and you touch it, it's going to be really hot. So those are some of its properties. We also have polymers. And polymers is just a fancy word for plastics, right? And again, we can think back to any examples of plastics in our lives, and there's so many of them, right? We can have phone cases or water bottles or the rubber on your shoes, right? All of these are examples of plastics, or examples of polymers. So they're soft, they're softer than metals, they're pretty flexible, but there's a big variety of them. And then lastly, we have ceramics / glasses. And for this, hi friends, feel free to move around chairs and tables if you need. There's also snacks in the back. All good. Totally understand. Anyway, ceramics and glasses, I like to think of ceramics and glasses literally just as like a dinner plate, in that you can't bend it at all, and if you drop it, it'll shatter. So it's very brittle, very hard. And the way we're going to kind of describe these, first is by going into different kinds of bonding. So we'll start, again, we had metals. So let's start by talking about metallic bonding. So the way metallic bonding works is we have all of our protons, in our atoms, and their electrons form what's called a sea of electrons. So we have all of these negative charges, but they're not like connected to any particular atom. What they're doing is they kind of just like float around, and they're like attracted in general to the, dense proton clump, proton and neutrons, but they're not necessarily bound to any specific one. And because of this, then these electrons are able to move back and forth, right? They're not bound to any specific proton, which means they're able to move back and forth. And that's what gives it its conductive properties. So it's conductive because of that sea of electrons. Also because of, these electrons aren't firmly bound, then that means that there aren't super strong bonds in between all the materials, which means that it means that they're able to be deformed a little bit, right? We're not like creating some sort of lattice where we have very specific bonds. They're kind of like floating around, which means that we're able to move them back and forth, twist it, turn it, whatever, and that makes it ductile. So we're seeing how we can relate the kind of bonding present to the properties of the metal. So the next kind of bonding that we can talk about is ionic bonding. No, actually, we're going to do covalent bonding first to math up. So we're going to do covalent bonding. So you guys take chemistry in second semester now, don't you? Okay. But from high school chemistry, you probably remember covalent bonding. This is sharing electrons. So we have like, two, whatever. We're sharing the electrons. This is genuinely a terrible drawing, but we're sharing it on the same valence, whatever it looks like. What this comes down to is sharing, well, electrons. Now note that this is directional, right? So we're not sharing in the sea of electrons, there's no specific directions that the bonding isn't occurring, but in the covalent bonding, we're bonding with an atom next to us. We have very directional. So because of this, because it is directional, that means because it's directional depends on the ions themselves, right? So depending on how strong these charges are, the strength of the charge will determine a lot of the properties of the bond. Bond properties. So what this means that we can change this charge that's in the covalent bonding, right? Depending on whatever material we have. And by changing that, by changing the number of bonds, all these quick things that we can change, we're going to change the strength of the bond dramatically. And if we have a stronger bond, that means it's going to be harder to deform, it's going to be harder to move, that's going to make the material a lot more hard. But if we have weaker bonds, it's going to be a lot easier to deform, it's going to be more ductile. And this kind of bonding is present in polymers, and this explains why we have such a wide variety of applications, such a wide variety of properties of polymers, because you can so quickly change the covalent bonding by changing the ions themselves, by changing the number of bonds present. Can you see? Do you want me to lower this down at all? Okay. By changing the number of bonds present. All of these means that we can change the strength a lot, very easily, and change it by a lot. This is typically done by non-metallic elements. And again, you think of polymers, you think of like carbon, and nitrogen and things like that. The last kind of bonding is ionic bonding. These are my favorite because I think they're kind of fun. And ionic bonding, again, we hear of this all the time. It's where you steal an electron. So we have some sort of positive charge, and then we have some sort of negative charge, and it goes yoink, and it steals the electron. In a very technical term, I think you should write that on the exam. And what this means, because we're stealing an electron, right? Like you give up the valence electron or you take the valence electron, whatever. Because we're stealing this electron, that makes it very, very strong. But once again, this is very directional. So we're stealing it from a very specific atom. So what we're going to end up with, let's say we have a metallic element, metal, and that's going to steal the electron. Oh no, it's going to give up electrons, give up E. And then we're going to have some sort of non-metallic. And this is going to take E. We're going to have some sort of lattice that ends up being formed, right? Here we have, I'm just going to do it in one direction to be safe. So we have all of these bonds going back and forth where we're stealing it from a very specific atom. But what happens if we were to, for example, apply some force to one of those rows? And now we shift this all down by one. Oh, actually, this is a terrible example. We're going to end up with something like this. I need to do a proper lattice for this example to make sense. Okay, so now we apply some sort of force, and we end up shifting this down by one spot in the lattice. Now all of a sudden, we have the green next to the green, and we have the orange next to the orange. I realized that these were terrible color choices for anyone who might be colorblind, so hopefully my circles make enough sense. We have these two lined up to each other. These are like charges, remember? And you have two of the oranges lined up to each other. These are like charges. And if you remember from high school physics or whatever background you may have, then like charges repel each other. So what's going to happen is as soon as you have a mild amount of deformation and you get those like charges next to each other, they're going to be repelled so hard, and we're going to end up actually breaking this bond. So that's going to separate. So what this means is that ionic bonding is extremely brittle. It cannot withstand very much deformation until it snaps apart. And this again relates to the material properties. So I'm just going to write here, very brittle. And this is seen in ceramics. And again, when I think of ceramics, I think of a dinner plate, right? As soon as you have any sort of crack that forms, it just snaps apart because you get a tiny amount of deformation. And now you have these like charges that are lined up against each other, and they don't like that. So they're going to push each other away, and they're going to end up breaking those bonds. Ceramics. Some other properties that go along with the very strong bonding in ionics is that it has a very, high melting temperature. And then these electrons, right, they're stolen. They're not being shared. They're stolen, which means that it's not going to conduct at all. So no conduction. It's kind of fun. Sometimes when you have a prof, I don't know if Dr. Sask ever did this, but they'll bring like little bits of like magnetic lattices and then they'll like show you how if you just move it slightly, then it'll all blow apart. It's kind of fun to play with. Anyways, so those are the three kinds of bondings. There's also the secondary bonding. So last piece of bonding here. So secondary bonding or van der Waals. So essentially what this is all molecules have electrons, right? And we like to think of our electrons as this nice little valence, but in reality, it's a bit of a cloud. They're just kind of like existing there in some sort of general area. And what happens is that for whatever reason, this cloud of electrons is going to orient itself ever so slightly unsymmetrical, and it's going to create a temporary dipole. So now we have this electron that's not fully centered, so we're going to have a bit more of a negative charge on one end where that electron cloud is, and a bit more of a positive charge on the other end. And now let's say we have that happen to another molecule nearby, right? Again, we have this electron cloud, but all of a sudden we have a positive charge right next to it. The negatives are going to be attracted to that, so it's going to form a secondary dipole in response. And what this does is we're going to get a very, very weak bond between them because we have a bit of a positive charge and a bit of a negative charge, so they're going to attract. These are really, really weak though, because, ionic bonding, we have those ions that are present. We have those positive and negative charges that are there. But in terms of van der Waals, these are temporary fluctuating dipoles, which just means that they're there just because the electron cloud shifted a little bit, but it's not going to be there all the time. So that means that it's very weak. Now, why do we care about this? That is because these bonds are often present again in polymers. So we'll have like polymer chain, and then I'll have another polymer chain, and these are connected by covalent bonds, but between the chains is where we have the van der Waal bonding. And this is why polymers as well can be very weak if we don't have very strong van der Waal forces. Sometimes it's kind of cool. You can get like extruded plastic where in one direction, then you're pulling on the polymer chains like this. So you're pulling on those covalent bonds and it's really, really strong. But then as soon as you pull it in the other direction, all you're doing is you're separating those chains based on the van der Waal forces and it has no strength at all. And I think it's kind of neat. But basically all we need to know about this is that it's the electron cloud that's shifting and makes them very, very weak. And that's kind of my quick overview on bonding in molecules. Any questions so far? Beautiful. Go for it. Yes, of course. That was a really terrible drawing on my part. So I like to think of polymer chains. Polymers are very long molecules. I like to think of them as spaghetti noodles because I'm not a very technical person when I think about studying. So we have this spaghetti noodle, that's a polymer chain, right? And we have another spaghetti noodle, that's a polymer chain next to it. And within the spaghetti noodle, right? Within the polymer chain, we have covalent bonds that are holding the molecules together, right? Like the CO, whatever it is, whatever, I took Orgo last year, so I actually forget everything about it. But you end up with these, strong chains. If you were to pull on it, along the length of the noodle, it's going to have some force resisting you. But between them, we're having those fluctuating dipoles. So they're having those van der Waal forces that are holding them together. But this is like, for example, if you have two spaghetti noodles and you have a bit of starch that connects them to, right? So they're held together a little bit, by those van der Waals forces. But it's not nearly as strong as the actual force of the covalent bonds that's holding the thing together. So if you were to pull on the length of the noodle, on the length of the polymer chain, it's going to be strong. But if you try to pull them apart in the other direction to separate them from the van der Waals force, it's going to be quite easy. Does that make sense? Beautiful. Okay, so next we're going to move into stress and strain. So there's my favorite thing about stress and strain is it's so easy to make puns about it. So I'll try not to like totally destroy all of you with it, but I just think it's really funny. And this is a really major concept in materials engineering in general because it describes the behavior of materials and therefore what uses we can have for them. So let's say we have some sort of block. I have a block. Wow. And let's say I apply some force on it. It's going to squish a little bit, right? We all know that. It's going to squish. But what if I have a really big block? And now I apply the exact same force on it. It's going to squish, but not nearly as much. It's just going to squish a little bit. Even if these blocks are made out of the exact same material, it's going to squish less if it's big than if it's small. So if we're trying to describe the behavior of a material, we can't just say, oh, it's squished by this amount, like its displacement was this much, if you want to be a bit more good words than just saying squishing it. But what we do as engineers is we have to find some sort of value to quantify how much it decreased in length by and how much force we were actually applying for, to compare these two situations. And that's where stress and strain come into play. So stress is given by sigma, and it's equal to the force over the area. So in this case, if we're applying the same force in both cases, we don't have the same stress because this area here is much smaller than the area on the big block. So that means that the small block has a higher stress, whereas the bigger block has a much lower stress because it is a much higher area. Note that the area that we take here, when we're talking about normal stress at least, the area here is the area that's perpendicular to the force that's applied. And now we can define strain using epsilon is equal to the change in length over the initial length. So what that is saying is essentially how much did it actually change in length by. So if this is its initial length, L naught, the change in length is however much it was squished by. That's delta L. So the units for stress, if we were to look into the units here, so this is newtons over meters squared, if you were to work in SI units, because newtons for force, meters squared for area, and that would give you a unit of pascals, which is what we typically refer to our stress in terms of pascals. A more common unit for stress, however, would be newtons over millimeters squared, and that gives you megapascals, which is equal to times 10 to the 6 pascals. So it's really, again, just important to know that these conversions exist, so when you're doing your questions, you have the right answer, or the right units. The units for strain are actually non-existent. It's completely unitless, as long as your units for delta L and L naught are the same. They'll cancel each other out. Now this also, so I showed you in compression, but this also applies in tension. So if you were to pull it, it's the exact same concept. You're pulling it, applying a tensile force as opposed to compressive, and you're going to see how much its length changes by. So there's a few different things that can happen when we apply this force to a material. So let's say that we have some bonds here. I'm going to make another lattice. Check. So again, I'm going to apply some sort of force, just on the edge, for example. I'm going to apply this force. Or we can apply it over the entire area. So I'm applying some force. And what's going to happen when I start to apply this force is the bonds are going to bend a little bit, right? They're going to get squished as I apply. Actually, for a better example, I'm going to be applying a tensile force. So I'm applying some sort of tensile force. So as we start, the bonds are just going to stretch a little bit, right? You can think of, for example, covalent bonding or ionic bonding, right? Those electrons that are being stolen or shared, like they're still connected to that initial atom that they were bonded with. They're just a little bit further away, and they're not happy about that, but they're just a little bit further away. So we're going to start by bonds stretching. Bonds stretch. And what happens is when these bonds stretch, as soon as you release that force, they return back because they're not happy being stretched, but they're like, whatever, we can go a little bit far away, but we're going to come back to what's normal as soon as we release that force. So they're going to get all stretched out. But then as soon as you release the force, it's going back to normal. But if you apply more and more force, what's going to happen is more force is that these bonds are actually going to break. Bonds break. If you want to be technical, then you can talk about the planes shearing. That's what you had in your slides, at least. So what's going to happen is we have, My computer's really old, so like the middle of the touchscreen doesn't work properly. So every now and again I go to write in it and it just glitches out. So bear with me. So we have, our lattice. I'll draw like a proper, hexagonal lattice. So we have our lattice and now we're stretching it. And what we have, right, if you think about this, is that we have these, or if you look at this, maybe, we have planes that are running along it. And what this means is these are just kind of directions where the bonds are closest to each other, where the atoms are closest. But eventually we pull on it so far that it's going to shift a little bit. So we're going to end up having something like this, where we've broken a bunch of these bonds. Those bonds are now broken, and the atoms themselves have moved from where they were before. If you were to release it, those bonds aren't going to go back. They no longer have that stretch of the bond that's pulling them back to their initial position. They're going to be stuck there in that nice little broken state. So what this means is this is irreversible. That face. And now we have words for what these are called. So when we're just stretching it and returning it, we call this elastic deformation. Elastic spring, if you have like F and X, it goes up and down and it goes along that path back and forth. We're nice and happy. But as soon as we have some sort of breakage going on, some sort of irreversible deformation, that's called plastic deformation. Plastic deformation. And it all has to do with the, again, with the bonding that's going on. So here's a question. I don't know if you guys are going to enjoy this in class participation or not. You can just stare at me blankly if you want. But what do you think would happen if we had plastic deformation to a ceramic material? A ceramic material, remember, is those ionic bonds. Go for it. Exactly. So we can see right here that as soon as you try and add any sort of plastic deformation to an ionic material, it's going to snap because remember we have those alternating charges, and as soon as we, as soon as we have that shear, they're going to be next to the charges that they normally have, and it'll break. So this is a bit of a hint that, again, ceramics don't have any plastic deformation. So we can start to kind of all represent this and kind of draw out these different kinds of deformation and stress and strain on our lovely little stress and strain curves. So these are like the cornerstone to materials engineering. Not really, but they're very important. We have stress on the y-axis and strain on the x-axis, and this really threw me off when I was first learning it because I was like, why, like, aren't we applying a force? Isn't that the dependent variable? Why? Or the independent variable should not be on the x-axis, but in reality, when you're doing these tests, is that you're controlling the rate of deformation, then you're registering how much force you need to apply to have that deformation. And we're going to have something that looks, well, we're going to start with elastic deform. So this is, again, relating very well back to the concept of springs from Physics 1D03. Again, if you have F, X, you're going to have some straight line with a slope of K. Oh, golly, go away. So we're going to end up with some sort of linear trend line that as you stretch it out, then it's going to, or like as you stretch it out, then it's going to have some sort of resistance as those bonds kind of want to pull you back in. They don't like being stretched. They want to return to their optimal bond length. But if you were to let go, you would return exactly where you were before. So you can stretch it out and then let go and return in the exact same spot. So this is our elastic region. And similar to, again, the spring constant for a Hookean spring, then we can quantify this slope. So I'm going to take that down here, and we'll say the slope is equal to the change in y over the change in x, which in this case is equal to the stress over the strain. And we call this slope Young's modulus. Young modulus, or the elastic modulus. And this just describes, again, how much elastic deformation and how springy it is, right? Now, after this happens, after we've gone through this elastic region, what's going to happen is now we're having again those bonds that are breaking, that are shearing. So the graph is going to start to even out a little bit and then fall down. And what's happening here is, again, if we were to release this, it's not going to go back to normal. So this is called the plastic region. And now on this graph, we can quantify a few different values. So again, we talked about the slope being the Young's modulus. This is only in the elastic region. That value, or that stress at which that transition occurs between the elastic region and the plastic region, is called the yield stress, or sigma y. The maximum stress you reach is called the ultimate tensile strength. And that's because basically anytime we do this test, you're doing tensile testing. So that's just the ultimate strength, the ultimate force you get when you're doing that tensile test. And then here at the end, that's the fracture strength, because that's where it fractures. It should be noted, so this is kind of like getting a bit more extra than what you'll need to know, but I think it's kind of fun. So as you're undergoing this process, as you're pulling a material apart, what's going to happen is, we start with something like this, and then it's going to get thinner and thinner as we get it longer and longer, right? You could think of like pulling silly putty or something. It's going to get thinner and thinner as you pull it up and down. So technically, you would think that as you continue to break it, this area is going to decrease. So if you're applying the same force, because you have a smaller area, the stress would actually continue to increase. However, that's a lot of effort. So as engineers, this is technically the engineering stress and strain what we're going over, where we only calculate it based off the initial area. If you were to calculate the true stress or strain, which is based on how the area changes over time, it would actually keep going upwards and it would look something like this, I think. I did one lab on it in second year and I was like, that's pretty cool. And then you never talk about it ever again because it's kind of a pain to calculate. But that's your fun fact of the day. Anyways, some other things to know about this graph is that the area underneath, if we were to talk about the area, so the area again is like, we can think of this as if we're calculating the area, right? So we're going to do area is equal to x times y, which is equal to the strain times the stress. And we can think of this as in terms of unitless times Newton over meter squared. And Newton over meter squared, if you were to do like a full funky, if you were to do full unit derivation, is also equal to the work being done. So the area under the graph is called the resilience, or maybe it's called the toughness, high key. Resilience? Okay, beautiful. I didn't want to totally goof that up there. So it's called the resilience, and this quantifies how much energy that it can absorb. So if you think of materials, for example, two materials, you have material 1, and then you have material 2, that they have the exact same failure stress, the exact same yield stress, exact same elastic modulus, whatever. But if one has a bigger area under the curve, it can absorb more energy. So there's a lot of good applications for things that can absorb a lot of energy. For example, if we're talking about our bones, we want to have bones that can absorb a lot of energy before they fracture. So we talk about the energy absorption as, for example, you undergo osteoporosis. I have my biomechanics midterm next week, which is what's on my mind. We talk about things like properties like this as it relates to the human body and applications like that. So we talked a little bit previously about, oh, OneNote, don't glance at me. Every now and again, OneNote decides that I'm actually touching my screen somewhere that I'm not. And then I'm unable to scroll, and it actually bothers me so much. Is it gonna work? We're just gonna restart OneNote real quick. Ignore me. There we go. So now let's start talking about the stress and strain curves for different materials. So I'm going to draw 3 here. Stress, strain, stress, strain, and then stress, strain. So we already talked about ceramics having basically no plastic region whatsoever. And that's because, again, they have ionic bonding that as soon as you start to deform them, those similarly charged ions are going to repel each other and it's going to snap. So we're going to have something that looks basically like a straight line, just going to be a straight line. So it has a very high Young's modulus. It has a very high ultimate tensile strength, but that's equal to the yield strength because it doesn't have any sort of plastic deformation. But it has very low strain, very low elongation. The next we're going to talk about is metals. So metals have strong bonding. They have metallic bonding, right? We still have those ions that are like the metals that are being bonded. That was really terrible wording. We still have the electrons that are floating around, creating those strong bonds with the different positively charged nuclei, but it's not quite as strong as those ionic bonds. So we're gonna have something that has like a decently high yield strength, but then it's going to enter a plastic region. Remember, because we have that sea of electrons, we don't have any specific directional bonding, so it can move around, it can adapt to a lot of these changes, and that's going to make it very ductile. So it's going to have the typical, quote unquote, stress strain curve. I'll draw it a little bit better. So we're going to have our yield strength, our ultimate tensile strength. And I like to think of metals as a nice happy medium between ceramics and polymers. Because now if we go and we think about polymers, remember those polymers are really variable, but they're largely held together by van der Waals forces, by covalent bonds that aren't necessarily, or like mainly van der Waals forces, to be honest, so that they aren't necessarily as strong as metals or ceramics, but they have a lot of that flexibility because these are constantly changing, they're constantly being formed, they're constantly, unforming because of those moving sea of electrons. So we're going to end up with something that looks a little bit like this. So this is going to have a low yield strength, but very, very, very high elongation. And you might be like, Sarah, what on earth is this funky little shape here? Why does that look completely different than everything we've seen before? And this is just kind of gets down to how polymers behave. So I'm going to relate this again to, let's imagine we have a bunch of spaghetti noodles. I took a course last year for my minor. It was like soft condensed matter. It's now being rebranded as squishy physics. And the prof literally talked about polymers all the time as spaghetti noodles, and now it's just ingrained in me. So we're sticking with the analogy here. Let's say we have a pot of spaghetti noodles, and all of these noodles are different polymers, right? In between all of these areas where the polymers cross over each other. Why not? Are you gonna let me zoom in, please and thank you? Oh me. Sorry, I talked to my electronics. Anyway, so we have all these spaghetti noodles that are crossing over each other, all these bonds, and in between each of these spots where the spaghetti noodles cross, again, we could think of like that's starch that's on the spaghetti noodles that's holding them together. So we have all of these van der Waals forces that are happening every time we cross over. We're going to get these forces. I'm too lazy. So we're going to get van der Waals. So when we start to pull them apart, so at the start, when we're applying some force and we're applying some deformation, we need to break all these van der Waals forces. And that's going to take a decent amount of work. So that's going to give us the elastic region. Right? As you pull more, you're going to need more and more force to break these apart. So that's where we get that initial elastic region from. But then all of a sudden, we've broken those bonds, and now we just have these long spaghetti noodles, but without really any strong bonds between them, right? So what we have to do now is basically, it's like we're taking the two ends of the spaghetti and we're pulling those apart. And all it is just untangling them. It's just like, really just like it's like if you had like my cord of my phone because it's charging, right? I've untangled it. Now I'm just pulling it apart. It doesn't take any force at all to pull it further. It's the exact same amount of force to pull it apart here as it is here. For folks who are online, I'm so sorry you couldn't see that. But it's really just untangling it, which is why so untangle. This doesn't take very much force. So this is low force and no change in stress either. And that's why we get this little horizontal region there, because we're just pulling them apart. That's all we're doing. But then eventually, now our polymer chains are basically lined up. We've entangled them enough that they're just lined up. And now what we have to do is we have to pull these apart, and that takes a lot of force because now we're pulling on those covalent bonds. Now we're trying to get those covalent bonds apart, and those are strong. And that's why we're going to get the final, like the final increase in stress, because it takes a lot more force to pull those apart than it was to break those initial van der Waals forces. So break covalent bonds, covalent bonds. That needs high force, so high stress. So those are the main concepts that I wanted to cover with stress and strain. Are there any questions? Go for it. Necking, yes. Yeah, it wasn't one of the main concepts, so I didn't like put it into what I was going to talk about, but 100% we can talk about it. So this kind of goes back to when I was talking about true stress and strain versus not true stress and strain. Let me just get the actual slide up so I don't totally goof it. But I'm like, where would it be? No one knows. Oh, I found it. Okay. So let's say that we have, when we're testing these samples, did you guys do the bonus lab where you go and do tensile testing of samples? Yeah? Okay. So we have samples and they're typically in some sort of shape like this, just to make it easier. Ciao. I'll make this actually a little bit easier. We just have some sort of eye, and we start to pull it apart. Again, I want us to think of, again, this is typically in the content of metals, but let's think of it in terms of silly putty again, right? So if you start to pull silly putty apart, or, I saw somewhere that people don't know what silly putty is. Do you guys know what silly putty is? Okay, good. I was like, what do you mean people don't know what silly putty is? But we're pulling silly putty apart. It's going to get thinner in the middle, right? So the same thing is going to happen with these metals, or with any sort of tensile sample that we're pulling, is that it's going to get thinner in the middle as we pull it apart. God, that's a terrible drawing. Heike, do you remember what lecture this was in? I want to make sure I cover all of the things that Dr. Sass would have talked about. No one knows. Never mind, I found it. We're all good. So this is going to happen with any sort of thing where you're applying that tensile load, is we're starting to get thinner and thinner in the middle. And as we do this, so as mentioned, if we were taking into account the area that we're being applied, that's being applied, right? We talk about stress is equal to force over area. So as we're doing necking, the area is decreasing. So if we were to maintain, for example, the same, if we were to account for this, for the same stress, then we would actually have a higher force. So as we're applying this higher force in real life, it should look something like this. We should have that graph continue to go up. But what happens is we're actually not going to be accounting for that. We're talking about the initial cross-sectional area. So what's happening is we're applying the same force that we were before, but now we have a much smaller area. So that's going to make the material feel it so much more because it's feeling so much more stress than what we were applying to it at the beginning for the same force. So it's going to feel a very, very high stress in those thinner areas, in thin areas. And because of this, and this is because it has same force, but smaller area. So it's going to feel a higher stress. And that means that we're going to start to get, this is where it's going to break, is in that necking area because it feels at higher stress. So essentially what's going to happen is as you continue to pull it apart, is at that one section, wherever it starts to undergo this necking process, it's going to quickly become the cause of fracture because we're going to get thinner and thinner and it's going to feel more and more force. So that means it's going to get thinner and thinner and eventually it's going to snap there. Does that make sense? Not quite. Fracking, that is not the right word. Necking begins to occur right around the UTS, right around the maximum stress that you see on the material, specifically like in metals when we're talking about this. Yeah, because that's basically whenever we talk about necking. It's going to happen right around the UTS. And that's because up until that point, it's still showing an increase in stress, right? Because we can still continue to apply more and more force without it like being super concentrated in that thin area. But then as it begins to get that thin area, that's going to start feeling a lot more force than everything else. So it's going to start um, being deformed at a much higher rate. So that's why we're going to go ka-chow, like that. Does that make sense? Beautiful. Any other questions here? Go for it. Yes.
Why that peak looks down or
Excellent question. So the reason it goes down is because, oh no, one no, why do you do this to me? Remember at the start, then we are pulling, we need to break those van der Waals forces, and that takes a lot of stress, that takes a lot of pressure, so we need to apply a lot of force. But then once they're all broken, we can actually decrease the force needed to pull them apart. Because after that, we're just untangling them. We're just kind of stretching out the polymers from their crumpled up state, but we're not actually breaking any of those van der Waals forces. So it needs less force, so less stress, compared to breaking apart those van der Waals forces. Does that make sense? Beautiful. Any other questions? Folks online, you're going to have to, again, unmute yourself. My speakers are not muted, which is going to be so funny if I said that and then my speakers were muted. I would laugh pretty hard. Alrighty, we're going to move on. So next I'm going to talk about fracture mechanisms, and then I'm going to talk about strengthening. And after that, we'll just move on to Q&A. Oh, I am in the wrong tab here. So let's talk about fractures. So a quick definition, right, is that you can talk about failure and you can talk about fracture. Fracture is when it snaps, is when it breaks, right? Failure, it just means it no longer does its initial function. So this can include fracture, but for example, let's say that I have, I don't know, this pen. It's actually starting to fracture. It has a bit of a crack there. But let's say that the tip just got like, I was like writing super hard, then the tip got like super blunt and it wasn't working properly. That could be considered a failure of the material because it's undergone like that wear and tear. So that'd be a failure, but it hasn't necessarily fractured. I think that might have been a multiple choice question on our mid-year exam. I actually don't remember anything from that because it was like December 20th. And it was just like, so, yeah. But it's important to understand the difference that failure isn't necessarily a fracture. So when we're talking about fracture, we're talking about things breaking, things falling apart. And there's two different ways that this can happen. So the first is a ductile fracture. Ductile fracture. So a ductile fracture is kind of what it sounds like, is that it's ductile. Crazy. So what happens here is that you undergo some sort of deformation, some sort of bending before it snaps. You guys want to hear this is unrelated. Do you want to hear a really funny plan? I came up with this myself when I was in the middle of Algonquin one time, and I've actually I peaked then. What do you call a bendy bird? Ductile. Thank you, thank you. I think it's really funny. Anyways, so we have ductile fracture, and what that means is it undergoes some sort of bending before it breaks. So a good example of this would be um again, silly putty. I keep coming back to that because I don't know, it's on my mind right now. But another example would be, for example, if you were trying to, I actually can't think of a single example of ductile fracture right now off the top of my head. It'll come back to me. But it undergoes some bending. So some things about this, because you have bending, then you have some warning signs ahead of time, right? So it happens a bit more slowly because we see this happening. Um, mm, mm, mm. There is, so bending, so we have large elongation. Because it happens slowly, we have large elongation. If we were to think of this in terms of a stress strain graph, right, we're going to have something like this. Because we have this large elongation, remember, if we talk about the area under the graph, that gives us our energy absorption or our resilience. So in these ductile fractures, we have high energy absorption. So that is one example. The other kind of fracture is a brittle fracture, basically the exact opposite. So what happens in this is that we don't have any bending. no bending. So we have very low elongation. And what that means is so that it happens very quickly. And then it happens, it's very unstable. Once it starts to happen, you really can't stop it. So if we were to think of a stress strain graph, it would look something like this, where you get very, very low energy absorption. And it just snaps. You have very little deformation. You just apply so much force that it snaps. So if we were to think of this in terms of biomedical application, again, I'm taking biomechanics right now. So if we're talking about bone fractures, right? If you were to be in a car crash and your bone just snaps in two, that would be some sort of brittle fracture. We don't have any warning, it just happens. But for example, if you were to have a stress fracture where you apply the stress continually over time and over time, that would be a bit more of a brittle fracture. So ductile fractures, of course, these can both happen in, a large variety of materials. Brittle fractures are very common in materials that have stress strain curves that look like that. So for example, in ceramics, the example that we have in your slide is like a hip implant material because those can be made out of ceramics, right? Whereas a ductile fracture can be more common in things like metals, polymers, because they have a lot more of that potential for elongation. And a good way that we quantify this, there's some snacks at the back if you want any. So a good way that we can kind of quantify this, or we can start to do calculations on this, is this concept called stress concentration. I mean, you're trying to remember this on the exam, just think that you're really stressed about concentrating enough to remember it. And what this is let's say that we have some sort of small crack that forms in a material. And, this can just happen, inherently we're going to have some areas that have slightly stronger bonds than others. So if we're applying the same force, we're just going to get some bonds that break a little bit first, right? Natural inhomogeneities in the material. So we start to get, I like to think of it as we get this small crack in the material. So like this is the material, and that's a bit of a crack. And let's think about the force that's being applied. If we're pulling this under tensile pressure, right? So what's happening is we're pulling in tensile pressure tensile stress is that we're pulling it up this way. So you can think about the stress concentration lines, if you will, is that we're pulling all along this line. We're pulling from the top, we're pulling from the bottom, right? And you can continue this line all the way through. But this area where there's a crack, if you try and pull here, you're pulling on nothing, right? You can't pull on nothing. If you think of, physics 1, 2, 3, you always have to have some sort of reaction force. So if we're pulling on both sides, what happens is that stress is actually, the pressure from that stress is going to go around the crack and then go to the other side. And you end up with something that looks a little bit like this. So what we see is that this stress that we're applying, this force that we're applying over the area is super, super concentrated at the tip of this crack. And that's the main concept behind stress concentration, is that we're having a lot more of that stress being applied at the tip of a crack than anywhere else in the material. And because of this, that's going to cause the tip of the crack to expand even further because it's feeling even more stress than anything else. And that's going to cause the crack to propagate through the material. A way we quantify this is using the stress concentration factor, KT. And this is equal to essentially the ratio of stress felt at that tip divided by the ratio felt literally everywhere else, the stress felt literally everywhere else. So this here would be sigma naught, and the stress in there is sigma max. You don't ever get values for that, though. We don't really have a way to calculate that stress, that sigma max, that stress that's max at the tip. So we actually are going to calculate this through 2 root A over PT. Now I hate this equation because the variables make no sense. But what this means is the variables that we use here, A represents the length of the crack. But note that this is the length of a half crack, actually. So let's say we have a crack in a foam material that looks like this. The length of the crack that we measure is actually just one side of the crack. So this would be A, but the total length is 2A. So if you're given, for example, an internal crack with a length of 2 millimeters, the A value would actually be 1 millimeter because A only relates to the one side of the crack because we're only dealing with the stress concentration at one of these tips of the crack. And then this rho t is rho density. Psych, you thought this rho t is the correct tip radius. And it's for reasons like this that I think it's really important to get comfortable using your formula sheet, because high key, if I looked at this equation, kt is equal to 2, root a over pt, I would have no idea what any of those variables mean. But this is the correct tip radius. So basically at this tip here, if we were to like blow it up, we have some sort of, radius, and maybe it's like, I don't know, 2 microns. I don't know I actually don't know what values those would be. But if you're trying to calculate kt, you plug it into this equation. So the next thing that we can talk about is how much I hate OneNote, and it's not gonna be happy with me right now. Okay.
Sorry, is the 2 root a over, is that just the math stress or is that the whole?
That is for kt. Sorry, I did not specify that. I'll add kt there. What are the units for the length of a crack? Anything relating to meter. What about for a crack tip radius? Yeah, so you just want to make sure that these have the same units, because then they'll cancel out. So for example, you might be given the length of a crack in millimeters, but the crack tip radius in micrometers. You just need to make sure you convert them so that they're the same. I don't know if Dr. Sass would give you 2 different units. Yes. So now we're going to talk about the actual crack propagation. So let's say we have this crack in a material. How do we know if it's going to move through the material, if it's going to get bigger? So so for brittle materials, remember, these are ones that have very quick propagation. We're given the formula sigma c is equal to 2 e gamma s over pi a all to the 1/2. And what are these things? So sigma c it's called the critical stress. And this is the minimum stress needed for the crack to continue. For crack propagation to propagation. And when I say crack propagation, what that means is we have some sort of crack, and then if it propagates, it just gets bigger, and then we have a bigger crack, something like that. What a glorious drawing. So then E, again, is our modulus of elasticity, so that's our Young's modulus. Gamma is a specific surface energy. And then A, again, is the length. So if we think about units here, the minimum stress, that would be in units of megapascals, for example, is equal to the square root of, again, megapascals times over meter, and then surface energy, you'd end up with megapascals, meter, and then surface energy would be like joules. High key for this, if I was trying to do units for this, I would convert it all to SI units. So I would convert it into pascals, and then I would have pascals, joules, and meter. I think it'd be joules per meter squared. I actually don't know, but if you put it into SI units, the units will work out. Do you have okay. So I actually don't know the energy for specific surface energy. I have to imagine it's joules per meter squared, but don't quote me on that. So that would be my tip is just make sure that you don't, because if you have megapascals and you have joules, remember a pascal or megapascal is newtons per millimeter squared, and then a joule is like a newton meter, right? Force times distance. So those might not cancel out if you keep it in terms of megapascals. So this is for a brittle material. And we can kind of quantify this. So remember, KT up here was our stress concentration factor. And now we have our critical stress. And now we have a very similar variable name to stress concentration factor. We can now call the stress intensity factor. And this is just regular K, not KT, this is regular K. And K is equal to Y times sigma times root pi A. And we typically assume that Y is equal to 1. And then this sigma is the applied stress. And then again, we have A, which is the length of the crack. And essentially what this is saying is, so previously we talked about the stress concentration factor, and this describes how, again, the stress will concentrate at the tip. We're talking about how that's going to happen. The stress intensity factor talks more about, based on that concentration, what's the likelihood that it's going to propagate. So they're very, very similar values, but they have slightly different names. And we can also talk now about another K value, because we love our Ks, is the fracture toughness, Kc. And this is showing, this is again, so we have the stress concentration factor. That's like, okay, how concentrated is that stress when we have some sort of crack? We have the stress intensity factor that talks about, okay, what's the tendency for it to propagate with that. And now we have a fracture toughness as like, how much can it resist that propagation? And I'll be so real with you, fracture toughness is really the only one that I use in any of my courses these days. But they like to give you all the other ones so that you can mess up all your Ks on the exam and make it difficult. There are uses for them, but fracture toughness is by far, in my opinion, the most important. And this is given by Kc is equal to Y sigma C root pi A. So this is the exact same equation as before, but now instead of the applied stress, this is the critical stress. So essentially the stress intensity factor, that's like, okay, how much or like how are we going to respond to this increase in concentration of stress? And the fracture toughness is, what's that maximum stress that we can withstand? How are we going to respond to that? So if you were to be asked to solve for the critical stress, for example, we have this equation up here for the critical stress, but we can also rearrange this equation down here. These are two different ways that they could ask you to solve for critical stress. And the reason we care about critical stress is because we want to know how much force can we apply to a material before any sort of crack could propagate. Let's say that we have some sort of material and we know that there's cracks with some sort of length. Like we have cracks of up to 1 millimeter in concrete, for example, because concrete is full of cracks. And we want to ask ourselves, how much stress can we apply to it before those cracks propagate and the whole thing falls apart? And that's why we care about these values. So there's this one graph that I actually did not understand until I think I was leading this review session in like third year, and I finally got it. But it gives you the fracture strength, and then crack size. And we have two different values here. So we have the yield stress. That is just a constant value, right? This doesn't depend on the crack strength or on the crack size. This is a material property. Yield stress is going to be constant. But we also have, if we were to rearrange the stress concentration or the stress intensity factor, we can get, the stress intensity, I guess, is equal to, or I guess the critical stress, we can solve for the critical stress, sigma C is equal to Kc over root pi A. And what this shows is that this is going to be, so this shows the maximum stress that it can withstand before it fractures. So if we have, for example, a high stress, so we're at a high stress, but a low crack size, we are going to be above the yield strength. And what that's going to do is that means we're going to yield. Because we've reached that yield strength, we're going to yield, we're going to bend. This is good. Yielding is good because yielding is something that we can see. If we have, for example, a bridge, we can see when it starts to bend. We don't want it to, but theoretically you can see when it starts to bend. And then if you have something that's low stress applied and low crack size, again, we're totally fine. But let's say now that we have a big crack and we have even just like a medium strength that's applied. So we know we're below the yield strength. We're like, we know that this material can handle it's below the yield strength, but we haven't accounted for is the crack size, so it's going to fracture. This is not good. So I'll really another classic examples in terms of pressure vessels. Let's imagine that we have this big tank that's storing a bunch of, I don't know, hydrogen gas, right? If we're up here and it starts to yield, it's just like we're like, ooh, that's not looking too hot. Maybe we have a small leak. We can fix that. But if you get down here and you start to fracture, all of a sudden you're having this thing blow up in your face, and that can be extremely dangerous. So it's in concepts like this that it's really important to consider the fracture strength and not just the yield strength. This also kind of demonstrates when we have ductile versus brittle fractures. So brittle fractures will be that cracking, that will be that ka-chow falling apart, right? In terms of a brittle fracture. So that would be in areas like here, right? Where we have, where our brittle, I'll write it here in words, brittle fracture, where sigma c is less than the yield stress. We're not getting that yielding. Again, we're going to have something that looks like this in terms of our stress strain graph because we have no yielding. But if we're in this region, now we're hitting the yield point first. Oh, actually just up to here. I do that too far. So we're going to hit yield first. That's going to give us a ductile fracture. So this is where yield strength is bigger. So you're going to end up with a stress strain graph that looks more like this. And that is my spiel on fractures. Any questions? Beautiful. Okie dokie. So now we just have strengthening mechanisms, then we'll open it up for Q&A. So for folks who might have arrived a little bit late, unfortunately, sorry, I'm just going to finish saying this before I get to your answer. Unfortunately, we totally lied when we advertised this. It's only going to be for 2 hours until 6. I cannot stay past that, but if you do have questions after this and you're like, Sarah, I wish it was 3 hours long, shoot me an email. I think somebody might have just said something online, but Heike, somebody had a question in person, so go for it. No such thing. On this one? Which curve? Like the curvy curve?
Yeah.
Yes, that's just the critical stress. Yes. This equation. What? Where? And then did somebody say something online? I was like very distracted, so I wasn't paying attention.
Yeah. Yeah, hello.
Hello, I can hear you. What's
Hi.
the question?
Okay. Okay, yeah. Sorry. So what happens in between the ductile and like brittle fracture region, like the non-shaded area?
Oh, high key. I just drew like in this graph.
Yeah.
Yeah, so I just basically drew this in the wrong spot because realistically, like that's really is gonna what happens. But what we think about is we think about increasing the fracture size and then we hit something. So it's more this region. That's all going to be the brittle fracture. Because as you start to increase the stress, as you start to increase the force, the loading that you're placing on it, this is the line that we hit first. Does that make sense?
Okay. Yes. Yeah.
Yeah, that was unclear on my
And so
part, so
above the yield stress, um, where it can take the fracture strength, basically like no fracture occurs, but the material can sort of have that wear and tear and it could fatigue. Is that correct? Like above the
anywhere
yields.
anywhere below the yield stress, below either of these failure stresses, then yes, we could have fatigue that occurs. And that will change. I did not actually add fatigue as one of my main concepts to review, so we can talk about that a bit more in the Q&A section if you want. But as soon as we hit either the yield stress or the critical stress, we're no longer going to have fatigue present because now we've reached a new failure mechanism and we're either going to yield or fracture.
Okay.
Does that make sense?
Yeah.
Beautiful. Any more? Yes, question. Like these graphs?
Yeah.
Yes. Thank you for catching that. Beautiful. Any other questions?
Yeah. Sorry. Will you have
Sorry,
time
somebody
to
asked
go over
something in
like
person. I'll get back to you online soon. Why did
Okay.
the area itself didn't technically shift. This was just me being bad, realistically, in my initial explanation, my initial drawing. Because realistically, when we look at this graph, what we're thinking about, come back. What we're thinking about is we're starting with 0 stress. We're starting at the x-axis, and then we're slowly increasing the stress that we're applying on it as we go up the y-axis. So in this region over here on the left, we go up, we go up, we go up until we hit some sort of failure mechanism, and we hit this green line, we hit this yield stress. So we're going to yield first. In the orange region, I initially drew it here because it was just a bigger area and I was lazy. But realistically, it's going to be this area underneath the graph that we care about, because again, we start with low stress and then we go up, we go up, we go up until we hit that thing, until we hit some sort of failure mechanism, and that's going to be the critical stress. Does that make sense? Amazing. Whoever was online, what was your question?
Oh yeah, sorry for interrupting. Are you gonna have time to go over like cyclic fatigue, that section?
Yeah, I can go over that. We'll talk about strengthening mechanisms, then I'll go over cyclic fatigue for sure.
Okay, thank you so much.
Of course. Alrighty, so we'll talk about strengthening mechanisms now. Whoa, thank you, OneNote. Strengthening. So when we talk about materials engineering, we can talk about the materials themselves, but a large part of materials properties depends on how we change it, how we modify the material. And I think this is where things get kind of fun. So the first thing we need to talk about is the concept of a dislocation. So whenever we talk about our lattices, we like to imagine a nice, pretty, chow. Oh, no, what are you doing, buddy? Oh, I don't like this. Yeah, this is really stressful. Anyways, imagine this is a nice, pretty lattice. God, I actually hate everything. Yeah, I'm gonna close OneNote and open it up again. Sorry, guys. I'm just gonna talk. We like to imagine that we have nice, pretty lattices, right? Oh God, that's so upsetting. Go away. Go away. But in reality, materials are full of defects. So instead of having a nice, pretty lattice with all of these bonds being formed, we're going to be missing atoms all over the place. So we're actually going to have something that looks a bit more like this. Right? And now we're missing this bond. And we can get into the reasoning behind this, that it has to do with the entropy of the system. It's actually kind of fun to do the derivation. You guys don't need to do that, but I think it's kind of fun. But we have this missing bond. And we represent this by a dislocation. It's given by the little cross, as you will. Sorry, guys, it's been a week, so I'm a little all over the place. But we have this dislocation. And if we were to bend this material, right, if we were to, apply some sort of force, let's say we apply a force along this middle plane, I apply some force. This atom can now hop over here, right? Because there's no other atom in that spot. So the atom can actually shift. And now we're going to end up with a new atom in that spot. And now we have a dislocation there. And you can keep doing this, and now the atom that was next to it will shift, and the dislocation is going to keep moving in the opposite direction that we're applying that force. And this is actually how we bend materials in the first place, right? We talk about those bonds that are stretching, but in reality, a large part of bending of materials is dislocations moving. When we get any sort of ductility, we want to talk about how the dislocation is moving through the material. Sorry, did someone say something online? Taking that as a no. So that's kind of the key concept here, is that in order to bend a material, it needs to be able to move the dislocations through. So I like to think of it. If you were to actually look at electron microscope images of dislocations, what it actually looks like, it's like the funkiest thing. So in this case, I drew a point dislocation, which is where we're missing one atom, but sometimes we're missing a whole plane. So let's imagine that we have a bunch of planes of atoms. So each of these lines represents, a bunch of atoms lined up in a plane. So let's imagine we have a bunch of planes of atoms. And then we're missing part of a plane down there, right? I don't know, this is a terrible drawing, but we're missing a bunch of atoms here, right? If you look at this on an electron microscope, you can actually see that plane of missing atoms, and it looks kind of like a snake. So as you deform a material, you can see a dislocation kind of as, I like to think of it as like a bit of a snake, and I'm going to use that as a bit of a drawing when I'm explaining these concepts. You don't really need to understand that per se, but just understand that we want to move these things through the material in order to deform it. So we're talking about strengthening mechanisms. We want to make things stronger. What we want to do is we just want to make it harder for that dislocation to move through the material. So The first process is called work hardening. And there's a bunch of names for this. Strain hardening, cold working, whatever. Did you guys do the copper rod experiment? Yeah, it's where you like bend a copper rod and it's super easy and you try and unbend it and you can't. That's an example of work hardening. It's really fun when you get a bunch of cocky high school boys try and do it. It's so funny to see them be unable to unbend it. But essentially what we're doing, your battery's running low. Your battery's running low. Give me a second here. So what we're doing in work hardening is we're going to bend the material a bunch, right? We're going to like you can undergo like rolling, for example, like cold working, but like we do some sort of processing method that bends it. And as we bend it, so let's just say we're going to bend it. And as you bend it, you actually add a bunch of dislocations. Add dislocations. Right? So we're adding a bunch of dislocations, but I like to think of these dislocations again as these little snakes. So we have this dislocation and it's moving through the material. Yay, it's so happy. But now we have another dislocation and another dislocation and another dislocation. What happens, these dislocations actually start to get tangled up in each other and they can no longer move against each other because they're all tangled up. And dislocations, I draw them as little squiggly lines because I'm just a squiggly line kind of person. But in reality, they're along a specific plane, right? We're missing a plane of atoms. So they're in a very specific direction. So it's not like they can just like easily go around the other dislocations because they're in different planes, they're in different directions, they're having a lot of trouble and they create a bit of a traffic jam. And because of this, it's really hard to kind of break those apart from each other and move them past each other. So that makes it harder to deform. There is, oh, I can't find the equation to it. So when we're talking about the strengthening that comes from this, the equation that's associated with this is the yield stress increases proportional to strain to the n. So strain is how much you strain it by. Actually, I have no idea what n is. I don't think I've ever seen this equation before. And I didn't see it in the slides. Yeah, anyone know what n is? Beautiful, because I was looking in the slides and I'm like, what, weird, they don't have one, but at the very end in the summary, then they include that. I'm just going to assume you won't have to know it. If anything, they'll give you a very obvious situation and you'll be like, whatever number that is, that's got to be n. Anyway, so that's work hardening. You can think of it as a bit of a traffic jam. I do have my notes from my second year materials class where we went into this in more detail. So if somebody's really curious, then we can go over that and I can find it. But anyways, the next one is grain size. And this is a bit, I really like this one, but it requires a bit of an explanation. So we talk about all these planes of materials, right? Or these lattices, right? So let's imagine that we have, planes of atoms going in one direction. But in a material, they're not all going to be going in the exact same direction. We have really big materials. These atoms are on a small scale. So we're going to have one region where they're going in that direction. But let's say the material started forming in this direction over here. We're going to have another region like that. And then another region where it looks like this. And you end up with these things that we call grains, which are just regions of material where the planes of atoms are going in different directions. Ciao. Ciao. So those are the different grains. And each of these boundaries between them is called a grain boundary. Crazy. Grain boundary. What? I know how to spell. So if we think about a dislocation, again, it's moving on a specific plane. So let's imagine a dislocation is moving along this little line here. It's going along, it's going along, it's going along, and then it gets to the boundary. And it wants to keep going in this direction, but it can't. What happens is it has to change direction and then change direction again. And doing this process of changing the directions as it crosses through a grain takes a lot of energy. It takes a lot of effort for the dislocation to be able to move and to shift. So every time it hits a grain boundary, the dislocation needs a lot more energy to move. It makes it a lot more difficult to move. So I'll just write grain boundary is equal to change in angle is equal to difficult. Sad face. Anyways, so if you can think about it, if we want to prevent this dislocation from moving because we want to make it stronger, we can just add more grain boundaries. So if we change it and now we have a bunch of small grain boundaries, right? The exact same material, but oh golly, with different angles. Now all of a sudden, instead of like being able to go this whole distance before having to change directions, every time that it moves, this dislocation is stuck running into more and more boundaries and has to change its angles more and more times, and it does not like that because it takes so much energy to change that direction. So by changing the grain size, we can increase the strength. And the equation to this is sigma y. So sigma y is equal to sigma naught plus ky d to the negative 1/2. So this is the initial yield stress without processing. Ky is some sort of constant. And then d to the 1/2, that's the average grain diameter. So whatever you're given, make sure that your units cancel out with whatever the constant is. And this is how this is how you calculate the change in yield strength from the grain size. Next, we have solid solution strengthening. And basically what this is, solid solution is, like if you think of a solution in chemistry or whatever, then it's like, oh, you have like a liquid and you mix like salt and sugar in, and wow, they mix together. But we can do this in solids too. And a very good example would be steel, for example. It's iron and carbon mixed together. So we end up with, we have like the original, lattice, but then you add in a different element in between. You can either add it in between, which is interstitial, or you can actually replace one of the atoms with something else. And basically, as you do this, this changes the size of the lattice spacing, right? Because you have, let's say, for example, we have our nice little lattice without the oranges in there. Now we add these oranges in here. We add these extra atoms. What this is doing is this adds extra atoms, and now the bonds are all being kind of, they're being a little squished. They're being pushed apart because we have these extra atoms in there. And because we've added these extra atoms, that increases the stress in the material. And this basically just makes the energies a lot more difficult to go through. You have a question? Yes. I'll keep talking about this though. And basically, the solid solution is just an extra atom that gets in the way of the dislocation, or less it gets in the way of the dislocation. Yeah, what this does is this just changes the bond energies. It squishes them, or it makes them like a little bit bigger. And that makes it difficult for the dislocation to pass through. So the way we calculate this, sigma y is equal to sigma naught plus ks root c. So again, k is just some constant, and c is the concentration of solute. So yeah, that's kind of solid solution. And then the last strengthening mechanism that I'll talk about is precipitate strengthening. Precipitate strengthening. And this is very similar, but instead of talking about like in a solid solution, we're adding atoms in between the lattices, right? In between the lattice spots, or either replacing an atom in the lattice spots. So it's a very small scale, and we're talking about the bond energies. But let's say we have some sort of lattice, right? Again, these are just, atoms going in one direction. And then I'm like, actually, I'm going to throw a big chunk of purple right in here. We're going to break those bonds. We're going to throw a big chunk of purple, and it's going to, takes up a really big, much larger space. So this could be for, a good example is when you're making steel, which is a very common material, especially at McMaster because we have the steel facilities nearby. But anyways, the point is you can add little precipitates of like different phases of steel within processing, and that's going to make it a lot harder. Because let's imagine that we now have a dislocation and it's going through the material, and then it runs into this thing, and it's like, how the heck do I move through this? How can I skirt around this? So I really like the drawing, and this is the kind of thing that I said that I saw. You can find videos of SEM images where it shows you like the dislocation moving through things like this, where you have some sort of material, and then you have these precipitates, and you'll see that the dislocation is moving, like if it's moving this direction, it gets stuck around them, and it tries to go on either side of that precipitate, and then eventually it has to end up like going on one side or the other, but it gets stuck on that. And Dr. Zurob, who you guys probably don't know, but he's like he's a chair of the materials department. Oh, go away, go away. And he condones this to like running into like a speed bump, where it's like you have to slow down no matter what. You can't just smash through it. So this is like oh, that's not the pen I want. This is like a speed bump. So it has a difficult time moving through. The equation for this, sigma y is equal to sigma naught plus K over L, I think. Where L, I believe, is the distance between precipitates. And you can think of this because if you have a very small distance between precipitates, this will be really big, so you're going to increase the strength. Because a small distance means that it's really hard for the dislocation to squeeze between them. Any questions about strengthening mechanisms? Go for it. This? This?
Yeah.
That's the yield strength. Yeah. Which we're trying to increase to make it stronger. So that's the main aspect of materials that I plan to cover. So as mentioned for folks who weren't here at the beginning, this is advertised again as materials, ethics, and design, I think. I only prepared materials because I was told I could only do that. Because I was like, hi, can I only do materials? I care a lot about materials. I think materials is amazing and super cool and very interesting and also a bit more abstract than the other concepts. But now that we're into the next 30 minutes of Q&A, I'm happy to talk about the other stuff as well. But if you ask me ethics questions, I don't think I'll be able to give you anything better than don't be a hacker. So the question that somebody asked about before was, oh, what was it? It was, oh, person online. What was that question that you had before you wanted me to cover?
It was cyclic fatigue.
Yes, cyclic fatigue.
Yeah.
Beautiful. Okay, so now we're going to talk about cyclic fatigue. So a good way to kind of conceptualize this is in terms of weight training, right? If any folks here go to the gym, you can maybe have like a one rep max on, okay, I'm gonna brag about my brother right now. He recently hit a 1 rep max of 315 for bench. It was crazy. So let's say he could do 315 for bench because he's freaking massive. So that would be his, for example, his yield stress. He can do that. You do it once, he's not going to break. But if he tries to do a lower value, let's say, I don't know, 200 pounds, 250 pounds, technically that's below his limit, right? But if he does it over and over and over again, eventually he's going to break down and he's not going to be able to do it anymore. And that's essentially what we talk when we talk about cyclic fatigue, is that you might not be at your fracture stress, you might not be at your yield stress, but if you have some stress that's applied to you over and over and over again, eventually that material is going to wear down and it's going to fail. So a way that we can kind of characterize this is, let's say we have some time, like we're going to plot the stress over time. So, if we're just doing one session, you can be like, okay, we're going to increase the stress, and then it's, oh, I don't want an arrow. We're going to increase the stress, and then we break, and that's all we're doing. Yeah, stress. But we're going to be doing this over some sort of time, and we're going to do it over cyclic. So let's say that this here is our yield strength, right? We're going to stay well below that. We don't want to yield, right? So we're going to stay below it, and we're going to do some sort of cyclic fraction. So some examples of cyclical stresses could be, for example, in any sort of reactor that is undergoing some sort of heating, or like, for example, a steel plant, you're heating and cooling the furnaces at a specific duration or time per day, and you're doing that every day. Or for example, in your bones, as you just walk on them, that's a cyclical stress that could cause, again, stress fractures and fatigue there. Or if you talk about, for example, what's another good example? I don't know, running shoes are another good example, right? Where like you might not, you can do stuff in them, but as you wear them more and more, they're going to break down. So we have some sort of sigma max that we're applying and sigma min. And you might be asking, Sarah, why is that a minimum? Why is that below 0 for stress? All that means is that max, we're going to be applying, for example, let's call this compressive. And now we're applying some sort of tensile force, right? We're just alternating between tensile and compressive, going back and forth, back and forth. This is just an example of going above or negative. It doesn't necessarily have to look like this. You could make your graph look something like this, right? It doesn't have to be fully centralized around 0. That's just how it was in the example, so that's what I was following. So we can kind of characterize this by saying the mean stress. So Can you write for me, please? Did you just die on me? Pen, did you? Ugh. Gosh, technology. Sorry, friends. As mentioned, I also have exams and stuff, so I've been spending a lot of time on my laptop, and I don't think my pen has enjoyed that. Okay, are you gonna write for me again? Did you actually just die? I'll start drawing with my pen, with my finger for a little bit. So we have sigma m, this is our mean stress, and this is equal to max, guys, I'm trying my best here, I promise, plus the min divided by 2. And this is just your standard average. If I wasn't being recorded right now, I would have some very choice words. Okay, so you work again? Okay, we're gonna keep using my fingers for now. So another thing we can talk about is the range. And again, you can memorize this formula if you want, but I think that it's better to just think critically about this. We want to find the range, right? If you think of range, if you think of like physics, for example, that's how far you travel. So this is just how big of a stress difference we have. So the change in stress, and that's just going to be the max minus the min. Gosh, this is terrible. I'm so sorry. And then the last thing we could talk about is the amplitude. So the amplitude is whatever our middle point is to the top or to the bottom. So that's just going to be amp what, is equal to the change in stress, so like this total difference, divided by 2. So those are kind of the ways that we quantify it. They're relatively simple formulas, and I encourage you to approach them more from a understanding point of view as opposed to a memorization point of view. Maybe it's a OneNote problem. Maybe we restart OneNote. Oh, my computer doesn't want to do anything right now. We're gonna, oh God. I can't even like turn it off and stop and okay, so you just don't want to open up OneNote. You hacker. Sorry guys, let me just yell at my computer a little bit. You guys can see all of my tabs. Oh no. Oh no. How do I open up OneNote if it, oh my gosh, I'm so proud of myself and my computer. This is actually really embarrassing for me. I feel like I should have really figured out computers by now. I had so many years of online school. Eh. Let this be your insight into the fact that upper years actually have no idea what they're doing either. Um, anyways, Ben, what are you doing? What are you doing? Okay, my pen has its light on, but it's still not functioning, so I think we just cry. So next we can talk about kind of the fatigue life. So let's talk a little bit more about these graphs. So there's some value, for some materials, there's a value at which no matter what, if you stay below that stress, then you're not going to have fatigue. So for example, if we're talking about I actually can't think of an example. There's some, basically, if you stay at a low enough stress, you're not going to undergo fatigue. So you can think of maybe a table, right? You can write on that table over and over again, and you can apply a little bit of stress to that table as you write on it, but it's not going to break no matter how many times you go on that table or how many times you sit on a chair. That stress you're applying, that isn't going to cause any breakage. So that's called its endurance limit. If anyone can't actually see me online, I'm actually having a mild mental breakdown at my pen right now, but that's okay. We're trying our best. So we have some sort of endurance limit, and basically we have stress and we have number of cycles, which I'll call N, and I'm too lazy to write number of cycles. So it's just going to be N for now. And if we stay below this stress, we can go on forever. We're never going to fail. But if we get above it, now all of a sudden we're going to approach that fatigue. And we can also get this line. So this is the endurance limit. I'm going to call it the EL. EL is the endurance limit. But now we have some sort of other limit, and I'll draw this in purple, that goes above. And I'm going to call this is the fatigue limit. What is this? What is this called? So I actually don't know what the name of this is, and I'm not finding it in the slides, but this is kind of the stress. This is the fatigue life. So I'll just call it the fatigue life, FL. So if, for example, we're at this number, because the x-axis represents the number of cycles to failure. So if we're at, this value that I'm drawing with my finger, if we're at this number of cycles, we can go above that endurance limit. We can still have this mild amount here, and we can do that number of cycles without reaching failure. So you can read it off of like the x-axis and being like, okay, let's say maybe we get to a lot of number of cycles. If we just get a tiny little bit above that endurance limit, we're immediately going to fail because we've reached that fatigue life. You can also read this by looking at the y-axis first and saying, okay, let's say we apply, such and such stress. How long can we keep doing this until, how many cycles can we go through until it's going to fail? So let's say we apply this stress, we can go this number of cycles until it fails. So a good example of this would be, for example, if we go back to the weightlifting example, let's say my brother, again, he can bench 315, and now he's going to start benching 100, just 100 pounds. He can do that for a very long time, but eventually he's still going to fail. If you were to bench, for example, 200 pounds instead, that's going to be a little bit higher up. He can still do that for a while, but then he's eventually going to fail when he hits some certain number of cycles. And that's kind of the concept behind this graph, and the concept behind fatigue life is that the higher stress you have, the less number of cycles you can have before you fail. Now, it should be noted that not all materials have some sort of endurance limit, and we can go back again to weightlifting for this. My brother cannot, even if he just does push-ups at body weight, he can't do that all day. Eventually, he's going to fail. So instead of having a graph that looks like that, golly heckers, we're going to have a graph that doesn't have that endurance limit. It just has some sort of fatigue life that goes down like that. So eventually, no matter how, why are you not writing? Shit. Now my pen works. Okay, we're so fine. We're so fine. So if we, no matter how low stress we have, if we do it for a certain number of cycles, we're going to fail no matter what, even if it's barely any stress at all. So these are really good to pay attention to, especially when we're think of materials designed for things that do undergo that cyclical loading. So for example, if we're talking about a big batch processor that makes, that mixes cookie dough for commercial cookies, right? That's going to undergo a lot of cyclical fatigue as it mixes every day, day in and day out. And we have to make sure that we use good materials that aren't going to fail under that loading. Or we can pay attention to the number of cycles that it goes through for a given load and make sure that it gets replaced at a good time interval. So a couple other concepts to go over in terms of fatigue is that kind of intuitively that if you increase the stress, then the fatigue life decreases. And then if you undergo some sort of surface treatments, so the very lovely name of shot peening or case hardening, those will both increase the stress amplitude for a given cycle to failure. So again, these should both be stress amplitude. So let's say that we have, stress amplitude, number of cycles to failure, and normally it looks something like this. If we undergo either these treatments, then we'd have something that looks like this. So again, you can either think of it in terms of for a given stress, you can undergo many more cycles until failure, or for a given number of cycles until failure, you can have a much higher stress or change in stress. And lastly, we want to just make sure that we avoid any sort of crack components, because as soon as you get a crack, then you're going to affect the fatigue life a lot, because it's going to fatigue a lot faster as soon as you have that crack formed. It's going to feel those stresses a lot more because of the stress concentration. So we call this the effective stress intensity factor. Okay, so I'll just call it effective K, and we call that delta K, and we calculate this as delta K is equal to K max minus K min. So this depends again on the different size of cracks that you have present in your material. But as time goes on, then this, the K that you have is going to increase because your cracks are going to get bigger and bigger. This is going to keep increasing, which means that you're going to fail a lot sooner. This is delta K. And that's the kind of basics behind failure, the kind of basis behind fatigue. Does that make sense?
Yeah, that makes sense. Thank you.
Beautiful. Go
Excuse
for
me.
it.
So K is like a sort of constant in this last graph.
In this last graph, K is, it's not a constant because it's continually increasing with time, right?
Yeah.
As you undergo this, the question for folks who didn't hear is K a constant? And it's not, because as time goes on, as you undergo more cycles, then K is actually going to increase because our cracks are going to be getting bigger. So K just represents, again, the stress intensity factor. So, you know, how much are we feeling those stress lines around the edge of a crack? And this just represents the differences that we're having as we undergo the cyclical stress. Does that make sense?
Yeah.
Beautiful. I don't have anything else
Excuse
to
me.
cover. I'm just going to keep here staring at people and staring at my screen until people ask questions. But somebody online said something. Go for it.
Hi. Thank you. I just had a quick question. Could you please re-explain the formulas for the yield stress when you talked about the two strengthening mechanisms? I was just having a hard time differentiating between the variables there.
Yes, 100%. So the question was, can you explain the formulas for yield stress when we're talking about the strengthening mechanisms? And I admit I did do a poor job on that because the slides are not great and I actually could not remember what all of the variables were. So that's fully on me. But essentially, what we're talking about in all of these cases, what we have is we have the yield stress is going to be equal to some initial yield stress before we have any sort of processing done, plus some value. And it's this value that's going to be changing. Oh my God, it looks like a smiling face. But it's this value that's going to be changing as we do the processing. And it's going to increase. So by increasing this, we're going to increase our yield stress. So there's a few different ways that we can do this. So work hardening, then again, with work hardening, remember, we're doing some sort of strain. We're bending the material. So this epsilon represents the strain. And I don't know what N is. I'm so sorry. If you're really dying to know, send me an email and I'll figure it out for you. But I don't see it in the slides, and I actually don't remember ever learning this equation before. In terms of grain size, now we have this value. So K is just a constant. So K is a constant. It'll be given to you. But D here is going to be the average grain diameter. And this is how, if you're given a formula sheet and you're given some question, you can try and relate them together, because you can be like, oh, I don't know which equation to use, but I know that I have grain sizes. Grain sizes have some sort of diameter, right? And it's the size of the grain that's going to affect its properties. Therefore, I need to find some equation that has a diameter in it, and that's where we see this D. Next, we have a solid solution. So this is where we have things mixing together in some sort of solution. We're going to have some sort of concentration, and that gives our C value. And then lastly, we have precipitate strengthening. And this is where we have big chunks that are in the material. So what we want to see how far apart these chunks are from each other. And that's given by the L. And then in both of these situations, we still have K values, and those are just random constants that will be provided to you. Does that make sense?
Yeah, that made perfect sense. Thank you.
Beautiful.
Just a
I'm
quick
glad.
extension to that. You mentioned
Go
that
for
there's
it.
going to be like, you would technically have to do a lot of unit conversions. How would you go about kind of managing that? Because there's so many different units and equations. So how would you manage all of that?
Yeah, so the question was, how do you manage all of the units and equations? So Dr. Sask might be nice enough to make you not have to do any sort of unit conversions, but maybe she will. I don't know. There's a few different ways you can manage it. So personally, whenever I'm given a question, let's say I'm given a bunch of words here in a question, I start, before I begin even solving it, I just write out all my values on the side. So for example, maybe I'm given yield stress is equal to 200 megapascals. And then I'm given like the radius is equal to 4 meters, right? So just by looking at these, and I think it's important to just understand the units. And then maybe I'll write next to this that this is equal to 200 times 10 to the 6 pascals. Just so that I know in my head that I can convert it into SI units, newtons per meter squared. Next, when you're solving the question, let's say for example that we have, oh golly, OneNote, why do you hate me? We're solving some sort of question. We'll just do a very simple example. We're trying to find Young's modulus, right? I think that it's always important to include units when you're actually calculating this. So for example, we'll say 200, we'll say strain is equal to 4%. 200, and then if you were 200 megapascals, and let's say we put in 4%, but 4% isn't like, that isn't a unit, right? We need to get rid of that percentage. So I need to convert that. 4% divided by 100 is equal to 0.04. So then I'd have 200 megapascals divided by 0.04, and now I see that there's no unit on the bottom, and I'll end up with some value in megapascals, and that'll be my final answer. So that's kind of the first step, or one strategy is to input your units when you're solving the equation, so that you can see when they cancel out. Another strategy, and this is probably what's best for you, like just putting them in, because chances are with Dr. Sask that they'll cancel out. But another strategy that you can use is to put everything into SI units. So remember, SI units are like newtons, joules, pascals, which is newtons per meter squared, put it into meters, things like that. So instead of having millimeters or micrometers or anything like that, you convert it all to meters. Instead of having megapascals, gigapascals, convert it to pascals. It's just a matter of like staying cognizant of it and making sure that you aren't like dividing meters by micrometers or something like that. Does that help a little bit?
Yeah, that helps a lot. Thank you so much.
Beautiful. If nobody asks me questions, I can just yap about how great materials engineering is and how you should all do it next year. But somebody asked me another question online, so you guys are unfortunately saved from that. What's up, homie online?
Wait, hey, are we given like the unit conversions in our formula sheet, or should we
Excellent question.
remember?
My best understanding, you're given this conversion.
Hmm.
So you are given the conversion between megapascals and everything else, but I think that's all you're given.
Okay. All right. Okay. All right. Thank you.
Of course. I'm gonna stop recording here for what it's worth. Can you work for me, computer, please? Please? Go for it.
Do you have any example questions? Could you do a question of anything?
Of course. Let me just have my computer start working for me again. Guys, I actually hate everything. I don't. I'm just frustrated by my computer. Let's stop sharing. Maybe that'll help. I'll start sharing my screen again once it stops glitching out on me. I can probably... Yeah, please take snacks, guys. I brought those snacks specifically for you. Okay, we're just gonna... Okay, I'm back. Sorry, friends. My computer actually hates me, so I'm going to stop recording. Stop. So there was a quick question to just go over an example question.